Um, when I say forest, I mean ensemble of trees, and I want to talk about how in scikit-learn we ensemble trees. So very generic forest. So scikit-learn commonly is used to solve the supervised learning problem. Oh my God. So where you're given x and y, and you want to learn this function that maps from x to y. In this talk, I'm going to have x be 2D and samples by n features, and y is 1D. How many of you have used the scikit-learn API? Familiar with it? Okay. It's a very nice interface where you could create a model, you could call fit to train your model, you call predict to predict, and a lesser known thing, you could call score to get the score. For classification, it's accuracy, and for regression, it's R2 score. So that's API. So let's jump right into it. What's a tree? All right. A decision tree is where, I have to speak really close. All right, a decision tree is where your samples start off at the root node and end up at the leaf node through binary decisions. So on the top, if your petal width is less than 0.8, it goes to the left. If it's more, it goes to the right. And it's going to end at a leaf and then use that leaf for prediction. So if it ends up in the orange one, it's going to be classified as the first class because that's the majority class in that leaf. Now, growing a tree, well, if you're at a node and you want to split this node into its children, you go to every feature, you sort that feature, you find the split point in such a way that it minimizes the impurity of your children. That means as a parent, you want your children to be more pure than you are. So this is the whole growing process. So that's tree growing. And it grows until it reaches stopping criteria. The way you control it is through these hyperparameters. In our decision tree regressor and classifier, there's max depth, min sample leaves, there's a lot of them. But today, I want to specifically talk about forests. We have random forest classifier and regressor, where you grow many trees. It's controlled by this hyperparameter called n estimators. By default, 100, so go to 100 trees. But if these trees are exactly the same, they're going to predict exactly the same thing, so averaging them would not be do you any good. So you want to create happy little trees where you do bootstrap sampling, which means you're going to sample with replacement. And for classification, for every split, we don't look at every feature, you're going to look at a subset of features. This adds diversity in the forest, which means it learns different parts of your data set. When you average them, it gives you a better prediction. So random forest, very cool. How do you implement it? Well, in scikit-learn, our tree building we don't write it in pure Python because it would be slow, so we write it in Python. How many of you are Python writers, developers? Yeah, Python's cool. I'm going to show you lots of Python. All right. Our Python releases the GIL, okay? Very important for later. Our forest building uses joblib, which is parallelized with joblib. What is joblib? Joblib it defines a very simple API for parallelizing code. Anyone can use this to parallelize the code. So by default, it uses multiple processes. In this case, I want to demonstrate the API. You create a parallel object. In this case, n jobs equal 4. That means it uses 4 cores. You have to delay your function because you want to make it lazy. And then you iterate it to, in this case, it just squares a square. It square roots a square. So it does this in parallel. So it's very simple to parallelize your code. How do we take advantage of this with tree building? Well, for tree building, we define the same object. But in this case, we prefer threading because our Python code releases the GIL. So we use multiple threads, and since the Python releases the GIL, we could take advantage of multiple cores. And so we do the same idiom. We delay the function call, and then this works. So this is what we do. This is the actual code of how we parallelize the random forest building. Okay, so random forest is very quick. What's cool was what was introduced in 0.21, which is histogram gradient boosting, which is our implementation of histogram gradient boosting inspired by LightGBM. So how many of you have used LightGBM, CatBoost, XGBoost? We have our own implementation in scikit-learn that's on par with LightGBM. I gave a very detailed talk about this 3 weeks ago, and I encourage you to look at it. I'm going to give a very quick elevator pitch of how this works in this one, very quick. Boosting is a very generic machine learning concept where you want to create a function. Your function you want to learn will be a sum of many little functions, and you train this iteratively. You build H0, and then you build H1 based on H0, and so forth and so on. Generally, there's something called attendees that does this, but today I want to talk about gradient boosting. When you think of gradients, you have loss functions. So for regression, we have least square and least absolute deviation. For classification, we have cross entropy. Now, once you have a loss function, which is a scalar value, we want to take the gradient. For example, least squared, it's this difference, and you square it, and you sum it all up. It's a scalar value. But the gradient is a vector value, which means every sample has a corresponding gradient with it, which I'll come to this point later. What do you do with these gradients? Well, for gradient boosting, you start with an initial condition. For least squared, you just take the mean. And so you just the most naive prediction you could think of, which is the mean of your training set, of the target of the training set. And then the recursive condition adds different functions to this prediction to make it better. This is not gradient descent. You're not updating weights. You're adding different functions on top of the previous predictions. Right? So this is a very different distinction. So I promise this is the last math equation I'm going to put on the slide because it's the end of the day, deliberately. So in this case, for least squared, h of m is going to be the negative gradient. And if you look closely at h of m of x, we're solving a subproblem. We want to find h of m such that it maps from x to y minus the previous prediction. So now we're solving a subproblem iteratively. So how do you solve h of m? How to get h of m? Well, since this is a do you want to build a forest talk? It's trees. And how do we build the trees? This is the hist part of the histogram gradient boosting. To form histograms, we need to have bins. And the first thing we do is bin our data. So in this individualization, the x is the row index, and the y is the feature value. And so to bin our data set, we take the last, in this case, 10 bins. The last 10% of data becomes 0. The next 10% becomes 1, and so forth and so on. So we discretize our feature space. After that, since each feature has its corresponding gradient, you could put them in these bins. So in this case, there's 5 bins. I'm going to sum them up and place them in their bins. So these are sum of gradients. We also need Hessians because the algorithm needs it. It's kind of hand-wavy. But after we bin it, this is where the speed of the outcome comes from. So this is, for an overview of the algorithm, we bin the data first, as we saw before. We make an initial prediction, which is a constant for least squared as the mean. Then since we have a prediction now, we could calculate the gradients by taking the difference. And then the tree building process will bin the data as shown like this. The cool thing about binning the data is that your split points are set in stone. They're on the order of how many bins you have. So since your feature space is now smaller. And the bins are ordered, so you don't have to sort your data. Once you bin the data, you don't have to sort them. So this greatly speeds up the algorithm for histogram gradient boosting. This is what makes LightGBM fast and what makes histogram gradient boosting fast. That's like the gist of it. So how do we make this? How do we implement this in scikit-learn? Could we use pure Python? It would be, as I said before, it would be slow. Could we use Cython? Yes, we do use Cython, but we use it compiled with OpenMP. All right? So I'm going to show you some Cython code, which almost looks like Python code, and I'm going to show you what it takes to make this parallel. Okay? So for bin data, once we bin it, we have to place the features in a bin, which is a binary search. So if you stare at this is binary search. But I tell you this is Cython, but if I didn't tell you that, it would look like pure Python. Right? So Cython is that cool. You know, you could write just Python and it would just run. In this case, if you look at the top, it's range. So this is in serial. If I want to make this parallel, I just change this range to a p-range. And this is all it takes to make this code take advantage of all your cores. Right? So it's very simple in this manner. So I'm going to show you a few more examples. When we split, when we find the best split, we go to every feature. You could do this independently. So we could do multi-processing on p-range. You could change the range of p-range, and this will speed up finding the features, finding the best split point for each feature. So it's cool. Next is n samples. You could parallelize over n samples, and you could do the same thing. This is all what this is doing is writing to memory, and we're doing it in parallel. And boom, it's faster. So compiling, if you write Cython and you want to make if you take advantage of all your cores, you could compile it against OpenMP, and it will just make slightly changes, and it will make it go faster. So it's awesome. So the boosting process, if you go back and look at the API for the boosting process and histogram gradient boosting, there is some parameters to control the boosting. Notice on the top, we need enable histogram boosting to import this. It's our magic, because our histogram gradient boosting is kind of experimental. So you have to import that to use histogram gradient boosting. Next, the learning rate and max iter are parameters based on boosting. Max iter is how many trees you want to add to how many steps of boosting you want to take. That's how many trees you have if you want to grow. The there's an environmental variable where you control how many cores you want to use. So you set this before you run your process. So if I want to compare, let's say I want to do some benchmarking. So one of the standard benchmarks we do is the Higgs boson data set, which is 8.8 million records and 28 features. It's a binary classification problem. If we want to run this and use LightGBM or sklearn, the time is about the same. It's around 38 seconds on 12 cores. The accuracy and ROC score is about the same as well. So this is as expected since our implementation is based on the LightGBM implementation. But the difference is that we write it in Python and the implementation is C++. So that's the only difference. Most of you just don't have 12-core machines. So if you have 4 cores, it's going to take more time, but it's going to have the same accuracy. So it's comparable with 4 cores as well. So this is how we parallelize the trees. For random forests, we have Cython, which releases the GIL, and joblib that does multi-threading. For history grading boosting, we use Cython and OpenMP. The big difference between random forests is each tree could be trained independently. Right? So you put in multiple cores and they train independently. The gradient boosting is trained iteratively. So in this case, to make it faster, we have to make the growing of the tree faster. And that is why we chose these techniques. Now, after we train these models of these trees, what can we do with them? After we train these trees, what can we do with them? Well, we could inspect them. In model inspection, we have permutation points and partial dependence. We also have plot partial dependence. So I want to show you what permutation importance is without any math. I'm going to show you with an example. Okay. Let's say I want the permutation points of the first feature of this data. This is just pretend data. I made this up. Right? It's not real. It's a classification problem. And I'm going to fit my data. And I'm going to score it. And so since this is classification, it's going to be accuracy. Accuracy. Afterwards, I'm going to permute the first column. So you see the first column was ordered here. I'm going to compute it. I'm just going to shuffle it. And then I'm going to score it again. So, and it's going to give you another number. In this case, 70%. I'm going to permute it again. I'm going to get 73. I could keep on doing this. You know, I could keep on doing this for as long as I want. And let's say I do it 3 times. And remember, the original score was 90%. So the definition of permutation feature importance is going to be the difference between these. So in this case, I take the difference, and you get something like at the bottom. The insight about this is if a feature matters, if you permute the score, if you permute the column, it will drop the score drastically because it matters. But if it doesn't matter, permuting the feature would not drop the score at all because it doesn't matter. So that's the basic intuition around permutation importance. So I did this quite manually here, but in scikit-learn, we have permutation importance, which would do this for you. So in this case, you shouldn't do it 3 times, but I did 3 times in the example, so I said n repeats equal to 3, but you should do it a lot more times. And what it returns to you is a dictionary, where the keys are the importances, which is the raw values that you saw before, is just the raw computed importances. And then for ease of use, we include the standard deviation and the mean of these samples. So let's look at this. Let's look at feature importance for a real data set. Real as in the Titanic data set. All right. We have fetch OpenML, which allows you to access lots of data sets on the OpenML server. And in this case, I'm accessing Titanic. This is new in 0.22. I could use asFrame equal to true, which will return a data frame. Okay? And afterwards, I'm going to add a random category and a random number into the data frame. Right? So these things are just noise. They do not matter at all. Okay? So I'm just randomly add things into it. How many of you have used pandas and scikit-learn together? Okay, cool. I'm going to show you something awesome. How many of you have used column transformer? Column transformer. Okay, I'm going to show you column transformer. I always like to plug this whenever I can, so I'm going to plug it now. I'm going to look at only like several columns. So this data set has categoricals and numerics, right? So I'm going to look at a subset of them. And since we're great data scientists, you know, we're going to train test split them. And this is the column transformer. All right, so I'm going to create a pipeline just for the categories. So in this case, categories has missing values. So I'm going to impute it with the word missing. And then I'm going to one-hot code it. So this only makes sense for categorical features. Right? You're not going to do this for numerical features. And I'm going to have something very simple for the numerics. I'm just going to compute the mean. Okay? So what the column transformer is, it allows you to create this single transformer where you could specify the categorical columns, and it will pipe in it will pass the data in these columns by name into the category pipeline. So this specifies that the category pipeline runs on the categorical features, and same thing for the numerical ones. If you could see it, yeah. After you have this transformer, you could place this into another pipeline, and then pass it into a random forest classifier because this is do you want to build a forest, right? So, and then you call fit. And the cool thing about this is xtrain is a data frame. It's going to pass through the column transformer, and the transformer is going to run different transformations based on the column name, and then it's going to fit. It's going to train your model. All right, so that's it, like a slight detour in column transformer. It's awesome. Use it. I'm going to advertise it. It's been around for like 2 years or something, and like, use it. It's awesome. Okay. The accuracy of this model is 100% on training, which sure, but the test set is 81%. So how many of you have used feature points from a tree before? So this, all right? So this is the feature points of this tree. All right? You can see that the random number is the most important feature. All right? So that doesn't make sense much, right? It turns out that the random forest is heavily biased toward high cardinality features because it has many different places. Since the random number has so many places to split, it's going to choose it more often than not because it has high cardinality. So what permutation importance gives you is a way to get feature importance. So you can run permutation points on the test set, and it will give you a way to, and then you can see that the random numbers and the random category does not matter in this case. So it gives you this power, and which is very nice. But before you go around and just like, ooh, I'm going to use permutation points everywhere, I'm going to give you some warnings. I'm going to show you with another data set. So this is the breast cancer data set where it's classification, cancer and no cancer. I'm going to train test split this. I'm going to train a random forest classifier because do you want to build a forest? It's going to have 97% accuracy, and I'm going to run permutation points on this. So what happens here? Well, nothing is important. Right? So like the most important thing is like 0.008, right? What's going on, right? Like what's going on? Well, it turns out most of the features are correlated. So if you have correlated features and you shuffle a feature that's correlated, the information is still there, right? You can still, so the score doesn't drop because the feature still is in the data set, which means that you don't get the proper permutation points from this model. From the permutation points. So what do you do about this situation is you see this big yellow block, they're all just correlated, and there's tiny little blocks on the bottom. Well, you just select one of the features in the block. All right? So it's a very simple concept, but it's very important when you use permutation points. So I'm going to select these features. I'm going to train it a random classifier. I'm going to do the train test split. So I'm going to train it one. It's going to be 97%, same exact accuracy as before. I'm going to do the permutation points again. And you can see that now stuff makes sense. The mean radius, the mean concavity, and the mean texture, these are important. So this is one way to inspect how your models behave with your features. So it's model inspection. So that's permutation points. I want to talk about partial dependence. All right? All right. I'm going to explain this without math again. There used to be math here, but there's no math anymore. So because it's the end of the day. So I'm going to have this data set. It's regression this time. It's a toy data set. I'm going to fit this model. And you notice that I want to find the partial dependence on the first column again, the first feature. So what I do is, you notice that the first feature is ordered just for make it easier. I'm going to set the first column to all zeros. And I'm going to predict. This prediction is going to give me 5 numbers because it's 5 columns. I'm going to take the mean. Let's say it's 0.1. All right? I'm going to do it again. Put the 1 in front of the first column, and then I'm going to predict again. So I'm keeping everything else constant and changing just the first column to a constant. And I could keep on doing this. I could do it for 1, 2, 3. I just keep on doing it. I can make a plot. Okay, so this plot, the plot turns out to be something on the left. So as this feature increases, the prediction increases. This means it has an influence on your model. It makes it go up. So this is the partial dependence. If it was flat, that means it has no influence over the predictions of your model. Okay, so this is the essence of partial dependence. So let's run it through the cancer data set we had before. We have histogram gradient boosting. Remember, we have to do the experimental import enable histogram gradient boosting. And I'm going to fit, I'm going to score it. It's going to be 97%. So I'm going to show you the plot partial dependence API. This plotting API is new in 0.22. I'm going to let's go through it. It's plot partial dependence needs the estimator, the data you want to train on, and in this case, I want to pass it n columns equal to 2 because I want 2 columns. Why? Because I'm going to pass features equal to these things. These are the top 4 features from permutation importance, right? Not by coincidence. And so I want to plot these 4 these partial dependence plots. So once I do that, I'm going to create this plot, 2 columns. It's going to give you all this stuff. And as you see that for all these features, as the mean radius, the mean concavity, the mean texture grows, as it gets higher, those features go lower. But let's say yeah, it's good. So as it increases, the probability of the cancer decreases as these things increase. Now, let's look for comparison. Let's look at what it looks like for the top 2 are the top 2 are the most important according to permutation importance. The next 2 are not important according to permutation importance, the bottom 2. So let's see what happens for that case. So the first 2 is what we saw before. The bottom 2 is what was not important. So increasing the mean smoothness of the texture error or more flat compared to the top 2. So it's kind of what you expect. If you look closely and squint, you notice that the plot partial dependence returns this is object. The cool thing about this API is that, well, plotting partial dependence is kind of computationally expensive. It's a lot of work. So the disp object stores these things inside the object. That means if you plot this and be like, it's ugly, I want to make the line thicker, all right? So I could set the line width equal to 4. I set the keyword of line width equal to 4 as a dictionary. Just for giggles, who uses matplotlib? Who loves matplotlib? Okay, I'll tell them that, I think. So you can set the line width is a property that you could set on lines, and it'll make the line thicker, right, on all of them. So what this did was, well, the partial dependence was not recalculated. It's already stored in the object, and I'm just gonna set the line width on when I plot it, I could plot it again without recomputing anything. There's more to this object. Remember, there's 4 lines here. So it stores the artist, which is in a grid, and you could do whatever you want to them. You could set the line width to 10, the line style to dashes, the set color to red. I could say hello world on the axis on the bottom, and you end up with something like this. So you could kind of go nuts, because you could go nuts because it doesn't compute anything. It just changes the style of your plots. So that's awesome. So partial dependence, we're going through a lot today, kind of like really quickly, but we have Cython. We use Cython and Joplib for random forest, Cython and OpenMP for parallelization. Inspection, we have permutation points and plot partial dependence. So these inspection tools are model agnostic. They don't have to be forests for this to work. All the stuff I have for model inspection, you could do it for any model you want. You could do it for linear logistic regression and regression and everything, right? So it doesn't have to be trees. And I do want to show this demo. That's why I had this. Since histogram gradient boosting is the newest estimator we have in scikit-learn, and Nick spent 6 months on it, and I want to showcase, and it sparks joy that it works so well. I'm going to share this joy with you by showing a demo, all right? End of the day demo. I hope it works. This is SSH into a 12-core machine, all right? Can you read that? Can you read it now? Okay, all right. So remember, I have the export. In this case, this computer has 12 physical cores and 24 threads. OpenMP is not good at handling multi-threading. I mean, not good at handling hyper-threading. All right. So I'm going to set OpenMP num threads to 12, which makes it so that it uses 12 physical cores. The script I use is the same benchmark I used for the numbers I got before. And this is run in verbose mode, which means that it's going to give you lots of detail about the depth of those little trees that are training, how long it took. If you look at the bottom, you see that 12 cores are being used, like 100%. So this is cool. This wasn't possible. This is possible because we can compile Python with OpenMP, and it's fast. It's great. I don't know when we want to watch this, but it works. Okay. And that's my talk. So all the slides are on this GitHub. I'm Thomas JP Fan on Twitter. You can contact me about things, and that's it. That's my talk. Thank you for coming.
Right. Thank you, Thomas. Any questions?
So I understand a lot of these are new to scikit-learn. A lot of these model evaluations, they're new to scikit-learn. Is there a reason why you implemented them? Do they offer certain advantages over other methods of model inspection, or is it just down to personal preference?
We want to include more. The model inspection field is developing. It's a research topic, and these partial dependence and permutation points has been around longer, and so we include them. It should be included, and we so happen to include permutation points for this release, I think. So we want to include more because it turns out inspecting your models and see how they behave is important to us. So these techniques, it's the beginning. Me personally, I do want more inspection tools so that you can inspect your models and get more insight about what's going on. So,
thank you.
Yeah.
So can you say a little bit more about this new gradient boosting classifier and regressor? Because I noticed this is something new, and this is very exciting because traditionally people will think scikit-learn is great for all those traditional machine learning stuff, except the gradient boosting tree because its speed is just too slow compared to the other two, right? Can we say now that it is comparable with the other two, or something like that?
It's getting there. So for certain benchmarks, it's the same speed as IGBM. What we want in the future, also for 0.22, it supports missing values. Right? So you could put in missing values and it works as well. So that's very cool. What we want more from it is native categorical support, because you could train trees much faster if there's a native way to do categories. Right? That's in general for any tree. And we want to support sparse. Yes, because one-hot encoding, sometimes even one-hot encoding and running through a tree, you need a very deep tree to recreate what will happen if you just natively have categories in your algorithm. So there's ways to, it's very good now for this. It's very good now, and it will improve as time goes on for the next release. We are working on these ideas.
Yeah. The gradient boosting classifier, gradient boosting regressor are still there.
Yeah, no, the old ones are still there.
Okay,
Yes.
so this is not a replacement.
No, they both exist concurrently. They're kind of happy together. I'll recommend you using this because it's been really good because it's written to take advantage of multiprocessing.
Okay.
Yeah.
So you can do like n_jobs, something like that.
Yeah, you could use njobs and set. In this case, you have to set the environmental variable.
Oh.
Yes.
Thank you.
Hey, Thomas, I've got a question. So I noticed that you used OpenMP for parallelization. I know there are other tools like NPI or CUDA. Why did you use OpenMP? Was it just most compatible with Python or something?
It's very easily available. We can't. Could you do this in CUDA? I haven't thought about that. I don't know. We're not going to power against CUDA. But for Python, it was very easy to get it to work with OpenMP. OpenMP. Like GBM also uses OpenMP, and XGBoost also uses OpenMP, so it's kind of standard. So we just ran it. Yeah, it was the best tool for the job.
All right, thank you. Okay, any more questions for Thomas?
So the DISP plotting API, is that going to be, is there a plan to integrate that into for the entire sklearn library, or it's just so far for this?
It's for, we do have 2 other plotting functions that also has this API. It's called plot precision recall and plot ROC AUC. So we have it in, we want to expand this API for all the plotting utilities. For every plotting utility from here on, we'll return the DISP object, storing the computation so that you could change the style after the fact and not recalculate. Like, this is the goal. Like, we will have a lot more in the next release. Yeah.
Okay, any more questions? Going once, going twice? All right, let's give another hand for Thomas.